Okay, we're going to talk about tensors in special relativity. We just shown that special relativity is a coordinate symmetry. In particular, it can be viewed as a rotation symmetry in the three-dimensional space and time, because Lorentz transformation can be viewed in some sense as a rotation. Of course, the space-time rotation keeps invariant the length with s squared, which has this funny minus sign in front of the ct term, the time term. And but still, it's just, you can view just a rotation. So therefore, we can talk us from all knowledge of rotation tensors. So tensors are just objects having different transformation properties under rotation. Okay. And physics equations are written as tensor, in this case, four-dimensional tensor, four tensors, and it's automatically be rotational symmetric. Rotation again means it's Lorentz symmetric. Therefore, it's relativistic. The equation will be relativistic if it can be written as four tensor equations. So therefore, our task is now to study relativity physics, to write relativity physics equation. It's just a matter of constructing four tensors. Tensor scalars, tensor vectors, tensors of higher rank. If we and then the physics equation within those terms will be automatically relativistic. Let's remind ourselves something we knew in Euclidean space, in particular three-dimensional Euclidean space. The basis vector will be ijk, and if a vector can be expanded in terms of basis vector, with coefficient being the components of vector, and in this case sum over ai ei. But so we'll always adopt the Einstein summation convention, so we'll not bother to write on the summation sign. So whenever you see the two i's, it's understood they are summed over. So therefore, if you talk about the scalar product of two vectors, each of them expand in terms of basis, and we take the base dotting to each other, and with coefficient ai bj. And for Cartesian basis vectors, we can choose them to be orthonormal. So therefore, ei ej is just quantical delta ij. And we can look at this relation, this ei ej equal to equal to 1, as some kind of to say that's the base vector in the Cartesian coordinate is its own inverse, because something usually times its inverse equal to 1. In this case, it times itself equal to 1, so therefore we say it's its own inverse. So now we have scalar products. We're replacing the ei by the quantical delta, and do the sum, doing one of the sum, just changing the j index to I. So therefore, the scalar product simply is summing over a component a1 b1 plus a2 b2, so on and so forth. And again, remember, vectors or tensor in general is defined to have some definite transformation property under coordinate transformation, or under rotation in this case. And so like the components A are related to A prime by this rotational matrix, and B are related to B prime by this rotational matrix. The important thing to note is that the A and B may be all different, but the rotation matrix is same for A and same for B, the same rotation matrix. Okay. So in other words, if I rotate 30 degrees for A, I rotate 30 degrees for B, same. And we say tensor equation have rotation symmetry if you write in tensors. Now we're going to go to generalized coordinate, for example, we go to Minkowski space, a 4D Minkowski space. You have a set of base vectors, and we add one, the time direction, we call it the zeroth components. And now the important thing is it's the E mu, E nu are no longer orthonormal. Okay, so they don't equal to 1 or quantico delta. But still, we can take these dot products of basis vector, arrange them into a matrix form in which the E mu, E nu is element of a matrix, mu nu matrix, mu element of matrix G. And so, for example, the G00 is just E0 dot G0, G01 is E0 dot E1, so on and so forth. So writing these dot products of the base vector collected together, we call it a matrix. You notice the diagonal element of this matrix are the length of the base vector, because E0 squared, E1 squared. The off-diagonal elements are deviation from orthogonality. If the two, for example, these two E0, E1 are orthogonal, it would be 0 here. So if it's not 0, it means that's a deviation from the orthogonality. Now again, in Euclidean space, which is talked about previous slides, in the Cartesian coordinate, the measure simply is, because this delta, quantico delta simply is 1, 1, 1 diagonal, and there's no off-diagonal terms. So it's just identity matrix. Now, the fact the base is now inverse, which means we can define a distinct inverse metric. So we define inverse space vector. Now label them. Notice now we can label them with superscript. The base vector are labeled with subscript, and of course they define that when they dot into each other, give you 1. And we can also similarly define the inverse metric by dotting into the inverse basis to itself. And that's now again the metric now for the inverse metric with superscript compared with the metric over there is a subscript. And you can show it takes, you need to use some concept, but anyway, you can show that the metric and the inverse metric again are, when multiplied together, you get 1. Now, the fact that we have two set of bases, the basis and inverse basis. So therefore, for each vector, we have two distinct kind of expansions. For example, the normal expansion of vector A in terms of basis and with some coefficient. Now this time I'll write the coefficient with superscript. Okay, so A mu, E mu, and mu of course repeated, are understood to be summed over. And those coefficients we call contravariant components of this vector. Okay. In the same way, we can expand this vector A in terms now with inverse basis with superscript mu, and its coefficient, in fact, we denote the coefficient with subscript. And those coefficient expansion are called covariant components. Well, why such funny names? Because the vector itself does not change under coordinate transformation. Remember we talked about we're doing passive coordinate transformations. The object itself does not change, but its component projections on the basis, on the axis change. So therefore, A mu will change, but it must change in a way opposite to that change of the basis, because when they multiply together, they get A, which does not change. So therefore, whatever the base change, it must be canceled by the coefficient change. That's why this coefficient here is called contravariant, opposite variation. While if the one expand in terms of inverse basis, you wouldn't be surprised to say those transform in the same way as basis. So therefore, A sub mu is called covariant components. Uh, Often we are lazy not always say we adopt a simple way to say calling tensor components tensor by the tensor itself. For example, we may say he's a contravariant vector. By this we mean it's a contravariant component of vector. Okay, but we don't bother to say components. So just be aware. Now, if we consider dot product, scalar product of A and B. Now, if we expand in terms of basis, then the basis then in terms of metric. So therefore, you have to add contravariant components multiplied by uh, the, the metric. If we expand in terms of inverse basis, and this will be the inverse metric. So therefore, again, inverse metric comes in with covariant components. Of course, you can do expand one in terms of contravariant, other in terms of covariant. Then, of course, the bases are just cancel each other with one. So the nice thing about if you write in terms covariant and contravariant, then there's no metric you need to comes in, and so the scalar product is a superscript nu multiplied b subscript nu, and nu of course summed over. So whenever we sum over an upper lower indices, we call that a contraction. It reduces the rank. You start with A and together each have a rank 1, together rank 2, but with a contraction they become a scalar product which have no indices, so reduced from 2 to 0. And also notice, compare these last two lines. B sub nu is same, so therefore whatever in front must be the same. So therefore G mu nu contract with A nu, give it A nu with a superscript. So in other words, what it does is this inverse metric managed to raise the covariant components to a contravariant component. So we can raise and lower the indices using metric or inverse metric. Okay. So we mentioned that the contravariant covariant component, they transform oppositely. Another way to look at it is the scalar product is invariant scalar. So therefore A and the contravariant covariant component must transform in a way that cancel each other's effects. Okay. So if contravariant, say let's transform a to Lorentz L, then the covariant components would have transformed as inverse Lorentz transformation, because then their scalar product will be unchanged. So if you look at A prime B prime, so A prime is transformed as a Lorentz transformation, and B prime was inverse because covariant, and then you put in the effect of these two L inverse, that simply gives you the 1 with indices lambda nu, which is like a Kronecker delta, and equal to just changing the effect, changing lambda to nu. So so A prime B prime is equal to, so it's unchanged. And then we say the contravariant transform was L covariant, but for a general tensor with different ranks, I mean, with higher rank, it may have, for example, two upper indices, one low indices. Then its transformation involves for the upper index, I have an L factor, Lorentz transformation factor. For the low indices, I have inverse Lorentz transformation factor. So anyways, for each upper index, there must be an L factor. For each low index, there must be inverse Lorentz factor. But of course, like any of these equations, the indices must match. See, I have mu, nu, lambda as free indices. So on the left-hand side, the right-hand side must have mu, nu, lambda as the free indices. All the rest of the indices must be summed over, like alpha summed over beta downstairs, summed upstairs beta, gamma downstairs summed over gamma. So it's always like this. In fact, you should know a very important result called quotient theorem, which assigns an exercise in 3.2 in chapter 3. The fact, for example, if you're given a relation a mu nu equal to c mu lambda rho b rho nu, okay, the rho are contracted, indices are contracted, so both sides have the free indices mu and nu. Now, if you know A is a good tensor and B is a good tensor, let's say, then the coefficient, the C mu rho, must also be a tensor. It was the quotient must. So it was any tensor relation. If you know all the tensors, whatever's left over, must also be tensors in order. So it's sometimes very handy if you know some parts are already tensors, then you can figure out the remaining part must be tensors. Okay, that's the end of lecture 3 here. The takeaways. We talked about transformation of electromagnetic field. We derived it. Yeah, but it looks very funny. It doesn't look like the transformation for coordinates or derivatives. So we wonder why such a form, which we, of course, we will answer later on. Then we introduced the geometric formalism of Minkowski, which uses a four-dimensional space-time with time as an extra fourth dimension, and then has a non-trivial metric, which is not the Kronecker delta. So, and then we say the general basis, the bases are different from inverse bases, so therefore there'll be any tensor or vector will have two separate expansions. Okay, and it's useful to have different expansion because the contraction between tensor components of a contravariant and covariant is simpler when it's written in terms of these two different kind of components. You don't need to write the metric and also we noted that the contravariant and covariant components of a tensor, they transform oppositely under coordinate transformations. Lecture number 4. Next time we'll talk about the physics in Minkowski space, and written in those terms, a lot of things much more compact. And also we talk relativism, momentum, and energy. In particular, relative energy is equal to gamma mc squared. Okay, gamma is just the same Lorentz factor. And also we've shown no object can travel faster than c, and also massless particle always travel at c. Okay, that's the end of this session.